So for the second half of the class, we're going to talk about the autoencoders. So what is an autoencoder and what is representation of feature learning? So the idea of representation learning is really critical to machine learning because of several reasons. One is human engineered features are costly. If you want to design a new set of features, you better know, have some kind of expert knowledge on why you would like to extract certain features and then validate them in some way. The thing about neural networks that once we have the deep representations, we have multiple layers, we hope that the internal layers capture capture the representation. They're actually finding the feature for us. And then if we do have these features, hopefully they are relatively robust. I would say invariant totally, but although in many so-called transfer learning tasks, we do consider or we hope that they're invariant to the task. But you assume that this is just an efficient way by training the network on task A. So here is like one possible architecture. Conceptually, you have some input and you have some labeled data that defines mapping the input to output as task A. And then given this task, so for example, let's say you have a lot of sounds here, sound events, and here are labeled sound events. You know that this is a gunshot, and you know that this is a car engine, and this is some bird call or chirp. So you now have a network that actually is trained to perform this task, and in the process, it has some set of factors or weights, so internal representation, latent state. People use a lot of terminology like factors or latent states or hidden states that is eventually mapped to a little kind of a decision network here that gives you the labels. Now, we hope that if we now switch tasks and we have task B or task C, maybe we don't need to retrain the whole network. We can basically keep this set of representations here. So now if our task is actually, we can even try to switch the data. So maybe now we plug in here speech or music, and our task is to classify emotions. Hopefully a network that was trained on related but different tasks and maybe different inputs will still extract something meaningful from audio. So instead of doing Fourier transform, or maybe after doing Fourier transform, instead of doing some chroma or Donet's representations, you will have a network that will find an efficient representation of the data. It was trained on certain tasks, but then this representation becomes an entity on its own, and now you can basically switch the task and just retrain the final classifier here. So this would be called transfer learning. Now, the other thing is that we might be able, hopefully, to learn these representations also on unsupervised tasks. And we mentioned this term before. Supervised means that you have the pair. This is input X, this is output Y. So supervision means that there is a teacher, basically, that's kind of the supervisor here that tells you basically if you're correct or not in your classification. If you don't have labeled data, then we might want to talk about other ways to do this, and this is what autoencoder is about. So the idea of finding statistically representation of audio is not new. Actually, there is a term called audio basis, which appears or has been practiced a lot in music and also in audio encoding and compression ways without or unrelated neural networks. And the idea of audio basis is that it's unsupervised method, so you don't have like labels to drive your process of optimization. It provides some kind of a geometric representation of audio, a little bit like Fourier transform, but it will be learned instead of designed with a fixed matrix. It is based on the idea that you take your measurements and you factorize them. So we'll talk about what is matrix factorization. It's also closely related to so-called latent semantic analysis in text. If you have heard this term, great. If not, then just know that such a term exists. And when I mention semantics in music or audio, it's a little bit kind of motivated by the similar use of similar mathematics in language, which kind of uses the word semantics. So latent semantic analysis basically tries to take a distribution of words over documents and extracts these word vectors or topic vectors. So topic vectors become basically the result of latent semantic analysis. So there will be our features of the representations. We have seen something like that. We mentioned topic vectors before when we spoke about the idea of distributions over nodes. In one of the previous lectures, I referred to some of the work that was done in UCD by one of the students of Lawrence Sol, and who estimated, or who did the work. Her PhD study was about estimating tonality using graphical models, or kind of a version of latent semantic analysis. It has this sort of a meaning overlap of semantics, but again, I wouldn't say that finding tonality or key is the meaning of music, but the term is there. So topics maybe in text have much more relevant kind of intuitive meaning of saying semantics means this is the topic that the text talks about. In music, we just kind of will enjoy the fact that we can use the same math. Much more common technique in statistical analysis of data is so-called principal component analysis, which has a name. A very similar derivation was done by Karunen and Loev. So these researchers came up with this so-called Karunen-Loev transform, which is application of PCA basically to audio. There are some other sophisticated methods which are shallow in the sense that they don't use neural networks like non-negative matrix factorizations, independent component analysis, and so on. So the idea is to find an efficient representation of your samples, of your data, that will be able to represent with some error your original measurements, but also provide some ways either to manipulate or understand or extract some knowledge from the data. In audio, it could be referred as audio basis. So what is our model? I'm kind of like jumping here, but away from neural networks. But I want to keep in mind as we talk that this is actually kind of a very simple version of a neural network, because you can think about A's as the weights of a neural network. S will be some kind of a latent state, and I will show it later, and X is our output. The only thing we don't have here, we don't have any nonlinearity. We don't have any activation function. So keep this kind of in the back of your mind when we going to go and talk about autoencoders in a second. But the basic geometric representation is the idea that if our samples, which could be either a vector of sounds, basically samples, an audio vector, or it could be an FFT vector or a magnitudes of FFT. This is our data, okay? But we want to represent this on a smaller dimensional space. So if we have n-dimensional input, we want to have m basis vectors. So this line means that each one of them is a vector. Each one is n-dimensional, but all you have is m of them. So you have a shorter vector here that will represent your data, and we assume that whatever remains, this error, is noise. So this is kind of one way of thinking about the geometric representation that tries to reduce the dimension of X into smaller m-dimensional. So n is our original dimension, so we want to reduce the dimension of X, which is n-dimensional, to a smaller dimensional S, which is m-dimensional. And we assume that whatever remains or the error is just a noise. So another way to write this is basically, if we think about this as, let's say, spectral slices, if this is a spectrogram, we assume that there are only certain templates or basis functions that create this spectrogram, and each one is actually a weighted sum of your expansion coefficients. The only thing that this graph actually does badly is to show that X is n-dimensional and S is n-dimensional. This should be much shorter. Okay, it's as long as this because each vector here is a span or linear combination of these vectors, but you have only a few of them. So this should be so the length of this should be the same as the length of this one, right? So you have these m vectors, and each one has your m coefficients that will recreate the first vector. The second vector will have the next m coefficients on the second time step. And this is kind of the idea of basis functions, the coefficients, and the measurements. One assumption is that all of these measurements are independent. You think about them as experiments, as an independent measurement, and these will be the expansion coefficients using this basis. So a little bit more graphically, if this is our spectrogram, okay, we might basically frame the problem as, again, this kind of matrix representation or the composition problem, where we have our original X here, and we want to represent it with only a few templates. Okay, so if this is a template, this is a template, this is a template, these are kind of like the typical sounds that comprise of all the other sounds, and we assume that each sound here is some kind of a linear combination of these possible sounds. These would be the weights, okay, and or activations. And the idea is that if we take this times this, we get this. So I hope this kind of a graphical representation, since we're kind of a little bit more familiar now with spectrograms, makes sense that, you know, each shape like this is basically a representation of some sound event, maybe a note, maybe a vowel, maybe, you know, some kind of a phoneme. And then assuming that there is just a small set of these basic shapes, spectral shapes, and that everything else you see is a linear combination of these shapes with these weights or activations. And in this case, we kind of have almost a very sparse representation. Basically, we have only, well, you know, this shape is represented by a lot of activations of template 1 and 2, and practically nothing in 3. Again, 1 and 2. This template is activation of template. This spectral slice is activation of template 1 and 3, and so on. Then only 1, only 2. And so why this is so? Well, that's kind of part of the whole idea assumption. And whenever it works, that's the magic of how the data is constructed, is that actually a lot of the sounds or the events that we try to analyze are mixes of small subset of events. So instead of you know, keeping all this data, we can just keep a subset of typical events. This approach statistically is called principal component analysis. And the way it's formulated is that we actually want to approximate our data on a lower dimensional space. So kind of, again, as a disclaimer or as a point, I mean, I switched notations here, so apology about that. So if we had a high dimensional data, n dimensional, in the original slides, it was n. So, but if we have this d-dimensional data and we want to throw this or project this onto a lower dimensional space, and we had m in the previous case, then we can have reconstructions from that smaller dimensional space versus the original data, and we want to have a minimal error. Okay, so how is it represented graphically? Let's think that our original d or original n is 2. Okay, so let's say our data is 2-dimensional, and it's distributed like this. Okay, So what would be the best way to represent it in one dimension? You can think about, because all of these are linear, there is a matrix multiplication, or in the two-dimensional case, the only way you can reduce the dimension is basically do linear projection on one dimension. So if you want to think about all kinds of lines that you can pass through this space and project the points to one-dimensional line, the question is which line we would choose, so that if we just consider that one-dimensional projection of this cloud to one dimension, we'll have the smallest error. Smallest error meaning that if you take the actual point and you find the projection on that one-dimensional line, you will find the best representation. So if I want to draw this approximately, let's say, and we probably want to have these lines going through the zero, because otherwise we totally will incur bigger error. So if you have multiple possible lines, sorry, they're supposed to be straight lines, right? Okay, pardon me. So now we'll project all the points into this line, right? So this will be the projections, or we project things onto this line, right? And then every point here will measure the error between the real point and the projection, between the real point and its projection, right? So these would be kind of the ideas that we will explore. So then the question is, what are the best directions? So we can see that this so-called principal component, or this axis that goes through the through that, sorry, I kind of like mumble. If your data is distributed as some kind of an ellipse, right, like a Gaussian, then this Gaussian has principal axis. So if we take our principal component as the principal axis of this ellipsoid, all the projections onto this dimension will be the minimal error. Then the second principal component will be the perpendicular axis. This is true only for these nice Gaussian representations, but we kind of try to take this idea and kind of apply this, even for data that doesn't exactly behave in such a nice way. So now I lost my mouse. Okay, so this is the projection. Basically, we'll find the principal direction, and now we'll project all these points onto this line, and that will be our lower dimensional approximation. There are algorithms like singular value decomposition, which is a method from linear algebra that allows us to estimate this efficiently. I mentioned already that this is used in latent semantic indexing and latent semantic analysis, known as KLT, current logic transform. And our goal will be to show that autoencoder with linear activation achieves PCA by basically running the autoencoder through this iterative process without an activation function. So this will be the goal of this presentation. Okay, so the KLT, or the PCA, what it does, we said, it tries to find this sort of a mapping where we want to find something about the A that will give us some nice properties about the Y. So the properties about Y, that we want to have is that the Y's are independent or uncorrelated, and that the error is minimal. We showed this before, that there is this optimal energy compaction. So the math, just to kind of hint at how a PCA is usually done, we calculate this correlation matrix between the Y's, assuming that we have some kind of an output here, and you can show that the autocorrelation of Y becomes this A transpose RXA. And then if we want it to be independent, so if we want this RY to be independent, that means that it's diagonal, okay? So now we have this expression. Now, what will be the diagonal elements? These would be basically the energies, or the eigenvalues, or squares of the eigenvalues of this decomposition. So if you think about this matrix, Rx, and you think about A as a bunch of vectors, which will be our audio basis. If you kind of remind yourself about the definition of eigenvectors, eigenvalues, basically what we have here is R times A is this lambda, the capital lambda, which is this diagonal values times A. You can move A to the other side. By solving this problem, this basically, we can do this with closed form solutions, just finding the eigenvectors or doing the singular value decomposition, the kind of equivalent methods. We can actually find the A's, and then we retain only some of them based on this, which are the strongest eigenvalues here. Those who have never seen that, it might be way too much information. But just think about, this representation, where this is diagonal. This is what we calculate. We calculate basically a correlation matrix of our data, and we want this, and we solve this eigenvector problem. This is how KLT or PCA is usually done. Okay, this is closed form. It's not iterative, but I mean, it works. I mean, that's what it is, and there are a lot of algorithms or implementations of PCA. And what I'm going to show is that we basically can achieve the same thing with autoencoder, with linear autoencoder. So this is just a reminder of the geometry interpretations. These would be our eigenvalues. The lambda 1, lambda 2 would be the eigenvalues of the previous slide. And these would be the principal components or the vectors that represent the columns of A. And we can then decide that we just keep the first one because the lambda 1 was the bigger one. So the eigenvectors are the principal axis of this ellipsoid. And if we have more than 2 dimensions, you have hyperellipsoid. And the first principal component is the line that passes through its greatest dimension. We can rank them, and we can decide how many dimensions we want to retain. So we have some kind of a trade-off between how small, or by how much we reduce the dimension of the data versus how much error we actually have. So what is the relation between autoencoders and PCA? I kind of jump back to the neural network graph, and I want to kind of now point out to this equivalence if we don't have any nonlinear activations. You can remember that neural network is basically represented as X times weight, and this adds up to being some kind of an output which sums together here, and then there is this nonlinear activation function here that fires. But now let's assume we don't have any nonlinear activation functions. So all we're left is basically matrix multiplication of X times all of these yellow kind of lines connected to vectors could be written as a matrix. It is actually a matrix. We have seen this. I don't want to scroll up back, but if you go to the previous lecture today and you look at the expression of softmax, in the exponent there was actually matrix multiplication. So if we don't have not the softmax, the sigmoid. If we don't have the sigmoid, we are actually just staying with this matrix multiplication with a bias or without a bias. That's an additional question, because bias can be just represented as one more input that is linked to all of them with the constant activation. So let's ignore the bias for a second. The mapping of X to the inputs of these neurons, if they don't have an activation function, this is just a matrix multiplication. So this becomes our A, okay? What we used to be W in autoencoder, what is W in the neural network is equivalent to this A, the audio basis that we were looking in the PCA. So this is how we would think about the autoencoder. We have the hidden states H here, okay? We have the nonlinear activation function F, okay? And we have the W here times X. Then we reconstruct this, and in theory we have another set of weights V, which is multiplied by H, okay? So this H times V will give you Y's, and of course the Y's might have their own activation function G here. So this is kind of the autoencoder representation. The autoencoder is, of course, a non-linear. You have the full-blown neural network with all the possible changes in the parameters. But the idea of autoencoder that we want to learn this, so instead of having a subset of y's, instead of having labels, we basically want this to reconstruct. We want y to reconstruct the x. So this will be the same dimension here, and our cost will be mean square error between x and y. So you can think about the autoencoder as basically some kind of a way to trick the usual supervised setting by saying, well, our supervision basically is a question, can you reconstruct the input? I mean, part of the trick here is that you want this to be lower dimensional, because if it's not lower dimensional, you can always trivially just map x to y. So you have a bottleneck here, and if you go through this bottleneck and then you want to reconstruct, you kind of have the same problem setting as PCA, that you have a dimensionality reduction here. So if you want to have now a linear autoencoder, which is kind of the idea and part of the homework, the exercise 3, is that if f and g are linear, basically what we have is this multiplication. We have x that is being reconstructed by v and w, and in many cases we basically just take v to be w transpose or the inverse. So if v is the inverse of w, the main question is just how do we find this w that creates a low dimension that we want? Okay, now it cannot be really inverse because this is not a square matrix, so we have to find some kind of a pseudo inverse. So there is kind of a trick to move between v and w here, but as a concept, you can see that this is really just, for linear case, a matrix multiplication, and then kind of a reconstruction in inverse with a pseudo. So if w is the encoding, this is a pseudo inverse of w, it will give you y. In PCA, we mentioned this solution. If you want to kind of check out the PCA implementations, either in scikit-learn or other libraries, or just do it yourself with linear algebra, you calculate the covariance matrix of X, you find the eigenvectors, and from them you construct your matrix. As a side comment, actually for some specific statistics of X, you can actually even show that Fourier vectors, the Fourier transform, is basically the best representation for a certain type of signals, especially if they're kind of like have this kind of periodic structure. So you can even derive Fourier transform from statistical principles. We also mentioned that the capsule coefficients could be also represented or understood. There's some papers that show the capsule coefficients are optimal representations for certain types of audio signals on the lower dimensional space. But the whole point is that PCA is a linear autoencoder. Okay, so the PCA's latent vectors are basically the linear autoencoder H. Okay. Now, why we then need to have neural networks, or what's the big advantage of including nonlinearity? There are some aspects. One is that there are some theorems that tell you that you can have practically any function mapping if you have a nonlinearity here. But also the other advantage is that with PCA, there is no point of having hidden layers, right? Because a matrix multiplication, if you have another matrix multiplication, they're all linear functions. You can collapse all these matrices basically one matrix. So you have a linear neural network. Basically, it cannot have multiple layers. But once you start introducing nonlinearities, there is actually a meaning, or it makes sense to go from one hidden layer to another hidden layer, and then we can expand this. So we can actually go through these deeper and bottleneck hidden layers with these nonlinearity functions and come up with much more powerful representations. So this is still an autoencoder. It can be just multi-layered. Okay, so we still have a moment to kind of discuss something that will be relevant to generating with these representations. Next class, we'll talk about an extension of an autoencoder, which is called variational autoencoder. So what is a variational autoencoder? Just in a few words. The variational autoencoder assumes that these states here, okay, we don't model them just as algebraic or mathematical operation. We now think about them as probabilities, and we'll have to explain. So there will be some kind of a disconnect here because we'll have to take these states and estimate parameters of some distribution. But for now, just think about the idea that if we train something like an autoencoder, and if this is now a probability instead of fixed vectors, now we can generate a lot of instances of these hidden states, and they will now, each one of them will map to different output here. I mean, for any autoencoder, of course, you can just, any combination, inner combination of these activations will come up with, will generate some output. So variational autoencoder basically tells you that you have a distribution also that you estimate over these states. Thinking about that kind of concept of randomly generating some activations here with a matrix that was learned, will generate a lot of audio outputs here. So this is an example of a variational autoencoder from Tim Gertner's lab, also here in UCSD, studying bird calls. And the idea was that he actually trained an autoencoder on these different bird chirps, and then he randomly generates spectrograms and inverts them. So kind of will conclude with this example, just to show you, each one of these examples that you will see will be kind of a randomly generated spectrogram where the representation was learned by a variational autoencoder on a spectrogram, and now it just keeps generating more and more chirps. Just make sure that we have the audio. Yeah. All right. Okay, so kind of got the idea that by learning some kind of a smaller set of templates and then triggering them, you can actually create sounds that, the quality is not perfect. And of course, the phase reconstruction here, whatever the Griffith limb or whatever phase reconstruction was used here, it didn't give us very clear chirps. These are basically bands of noise instead of having sounds that kind of sound more musical maybe or voiced. So these are basically just, the resolution here is not perfect, but you can see that you sort of learn the statistics of some sound source, in this case bird calls, by finding these templates. And the way to do these templates is by basically training a reduced set of encodings by passing your original data through a bottleneck, and that bottleneck will tell you how many templates you want to save or store, and then you can retrigger them to create a lot of variations. So we'll kind of continue with this next class, because the critical element of how do you model the trigger functions or the probabilities here on the, I'm trying to go back to the previous slide. How do we model the probability over the latent states is actually the basis of the generative models that we want to talk, which will be the variational autoencoder, the GANs, the generative adversarial networks. They all kind of take a little bit the idea of autoencoders and PCA and put it in a probabilistic framework, which will be our next step. Again, I hope it kind of gives you and intuition and motivation of what are the acoustic problems that we're trying to solve, and encourage you eventually to kind of go dive deeper into the math in later classes. Okay, so I will stop here and take some questions, and I hope that was interesting and clear enough to give that picture.